Hello all, let's start section 5.2. Let's talk about volumes, how to find the volume. First, the volume of a solid object. Then later we talk about finding the washer and all kind of formulas. This lecture is really important. The only chapter that needs a lot of work, and calculus 1 is chapter 5. That's why at the beginning of the semester I went a little bit fast, but now you see I'm taking my time and I only gave you one section or maybe two sections per week. I'll focus on this lecture because I do a little bit of proof for you to find a formula based on calculus for volumes. Then you are not required to learn the proof. You will just remember the formula. Then we solve different problems for this section. To start with, there are some shapes that maybe it's really easy for you to find the value of those shapes. For example, if I even my drawing is not good. Let me change the position of my computer a little bit, then draw for you. Maybe I can draw it better that way because let me erase this. For example, if I ask you to find the volume of a shape, a cube, or a rectangular shape, like this, like a brick. If I ask you to find the volume of this shape, a 3D object, based on the geometry that you learn in school or high school, you may able to find, it's easy for you to find actually the value of this shape. Or even if I give you a cone like this, because you have a formula to find the volume of a cone, you may calculate. Or if I give you a sphere, which is really difficult here for me to draw a sphere in 3D for you, if I show a cross section in it, maybe you think it's a sphere, like a ball, baseball, right? Excuse me. You have formula for this in geometry, and you can find the value easily. But if I give you a shape like this, I'm trying to draw it nicely for you, then it's really difficult based on the geometry to find the value of such a shape, correct? Then we need here, calculus gets involved to can find these values for you. That's why you're studying calculus. Now, I'm erasing all of these because we don't need, and I will start how to find the volume of these kind of shapes, which we don't have a formula in geometry for. Let's draw another shape for you. I want to draw another shape for you here, and let's discuss this shape. I'm trying to draw for you a three-dimensional or 3D shape, which is not easy with the pen. I don't have a graph paper, really good graph paper to use it, but I'm trying to draw. Let's think about this shape. One side is a smaller, one side is big, and it's a 3D shape, right? If I make it 3D for you, hopefully you can see that it's a 3D shape, right? I want to find the value of this shape based on calculus. And it's a solid shape. Let's remember, we are dealing with solid shapes now. If you remember when we start with the areas, how to find the area under a curve, we start using the Roman sum, right? For example, this is an interval AB. We start with this. First, dividing the area under the sum to rectangular shapes, right? Then add all of them, and we were able to find the area under a curve, right? That's we call it the Roman sum. Now, using the same method, I want to drive a formula for you how to find the volume of a shape using calculus. Just focus on this proof actually, because this proof you will understand why you are using that formula. Don't just copy and paste the formula and calculate. That's why I want to do a proof here for you to show it to you how this formula comes in and why you are using it for different objects, right? Let's think about this. Let me use a different color. Let's take a small slice, or let's do a cross section in our object, right? When you cut an object, we call it cross section, right? I did here what? A cross section, correct? This is my cross section. If I shape this cross section for you like this, and if I bring it outside, here, show it for you, turn it around like this. The cross section of this object, if I want to find this, actually I'm here looking for the area to find this area, correct? Because it's a 3D object, correct? Because it's a 3D object, this one becomes Z, this one becomes Y, because it's a 3D object. You have to consider all X, Y, Z here, correct? Now, the area or the surface area, even you can call it surface area based on X, here gives you Y times what? Y times Z, correct? Remember this. Now, because I'm looking for the value, I'll take a slice of this object, this shape, like this. I'll take a slice of it, and I want to find the volume of this slice. If I can find the volume of one slice, and I divide my object like the Riemann sum to small rectangular shapes, right? Why we are taking a small? Because we want to make a rectangular shape actually. It's not rectangular, you see? When you take a small slice, it means you are taking, you're trying to change your shape to a rectangular shape, right? And if I add all those volumes, I can get the volume of this object, correct? Now, from here to here, you can name it delta X. If I bring this section out for you and make it, zoom it a little bit, try to draw it nicely for you. It's really difficult to draw with no tools. Think this is that slice that I brought it out from there, correct? That's your slice from there. Correct? This thickness, I'll name it delta X. Correct? And this is your surface area. Or if I do another cross section and I take an arbitrary point, xi here, then the volume of this rectangular shape, the volume in that particular slice, if I name it VSI, correct, equals the surface area of that arbitrary point, AXI, with a star, correct, times delta X. Because we know the volume of this object, a rectangular shape, is X times Y times Z, right? X times Y times Z gives you the volume. But your X is here, delta X, because you take a tiny piece of, or a tiny, when I call it slab, a tiny slab of that shape. And you first try to find the value, correct? After that, you are adding all those tiny slabs to each other. It means you're looking for the sum of those, and it gives you the volume of the actual shape, that which is this shape that I'm looking after, correct? Then I can, if I want to find out the volume of this shape, my formula will becomes V, the Riemann sum will be V equals I equals to 1 to where? To n, and slides. We are trying to make it a lot of slides, tiny, tiny slides or slabs to can add of them. My formula, AXI, my arbitrary point, times what? Delta X. You shouldn't forget that you need here a limit, right? And n approaching to infinity. Limit n approaching to infinity means you're taking small pieces, so many of them, and you add, and it gives you approximately the volume of this object. Now, I think everyone knows how to write this notation as an integral, correct? Everyone knows how to write this notation as an integral. Then you can write a formula here that V equals integral from A to B in a closed interval. It's a closed interval. AXI becomes as a AX, the surface area, and delta X changes to what? DX, correct? AX is, remember, cross section area, and your dx is the length. Correct? Your dx is the length. Your ax is cross section. This one will be for you a formula to calculate or to find the area of different shapes in calculus. Correct? I will go really slow. The examples that today I will do here, some of them is not maybe in your book, because in your book, immediately they jump to a function and they just calculate it for you. It's really nice, not nice way to go. That's why we have lectures for you to make it easier for you. Now, one thing that you should see here, when I draw all these shapes, they are perpendicular to the x-axis. All the shapes, they're perpendicular to the x-axis. If they are not perpendicular to the x-axis, I cannot find the value. They should be perpendicular to the x-axis, or it may be perpendicular to the y-axis, correct? If it's perpendicular to the y-axis, later I'll discuss it with you how to change your function. But right now, what we do, all the shapes, they are perpendicular to, or my cross section is perpendicular to the x-axis. You see, this is my cross section in this black area. If I draw here x and y, all those axes, you see this one is perpendicular to the x-axis, correct? Now, what formula I have? V equals integral from A to B, AX dx, correct? What about this? If I draw here a cylinder for you, I'm trying to draw it good. And this is my cross section, correct? And this is my bounds. Let's name it, for example, from C to D. Here you see your cross section is actually perpendicular to the Y, not to the X, correct? Then when you set up your integral, you should set this way. V equals, for example, from C to D, be careful with your variables, AY dy, correct? Here you cannot say AX dx. Now, proof was not important. That's your formula. I will do only one simple example how to use this formula for you. Then later, of course, I'll make it a little bit difficult like your book, and we deal with different shapes. Let's do an easy example. Example number 1. I'm trying again to draw. This example, I give you a graph or a shape. Here, let's put 1, here -1. Trying to draw here a cylinder for you. Like this. Maybe here like this. Is that good? Like that. Correct? This is a cylinder. And if I show it as a 3D for you, this point is 1 and this point is 5. This is your interval from 1 to 5. I want to find the volume of this cylinder. Look, if I do a cross section here, like this, if I cross a cylinder, the shape that I get, this shape, if I bring it out for you, it's actually a circle, right? The cross section of a cylinder is a circle, correct? The surface area for a circle, the formula for the surface circle of a circle is A equals pi r squared, right? For me, this one here will be AX equals pi. How much is R? Your R from here to here is 1, right? R, sorry. Your R is actually 1 squared. It means AX equals what? Pi. Now, if I have my AX, if I set my volume formula is V equals from A to B, AX dx, correct? Then I can write V equals integral from where to where? You see, from 1 to 5, that's your interval. From 1 to 5, AX, how much is AX? Your AX is pi, right? Pi dx. Then you can say V. Everyone knows pi is a constant, you can push it out, right? Then V equals pi integral from 1 to 5 dx, correct? Which V equals pi times integral of dx gives you x. From where? From 1 2, 5. If you plug in the values here, then V equals pi times 5 minus 1, correct? Or V equals what? 4 pi. That was a simple example for this part, correct? Sometimes, I'm sorry, it's broken. I don't know why it went out, but now we are back. This was the easiest example that I could do for you to find the value of an object, or in our case here was a cylinder. Now, before doing more examples, let me explain something for you. Let me draw something for you. Here is your x-axis. I'm praying to go back to face-to-face classes to can avoid all these problems that right now I'm facing. I wish our class was face-to-face. You would enjoy the class. Let me draw here for you a rectangle. If I rotate this rectangle, even different color, if I rotate my rectangle about x-axis like this, correct? The shape that I'm getting by rotating this will give me a cylinder, right? Like this. I'm not inside the class to show it with my hands to you, but when you rotate a rectangular shape about the x-axis, it gives you a cylinder like this, correct? Next one. For example, I have half a circle. If I rotate this circle about the x-axis, the shape that I'm getting here will be actually, think it's a sphere, right? If I do a cross section here for you, it gives you a sphere. Or some more easy shapes. For example, this is your x-axis. You have a triangle, a right triangle here, right? If I rotate this right triangle about x-axis, definitely all of you, you know what will you get from this shape? This shape is really easy. It will gives you a cone, right? Or maybe this shape. These are the shapes or the types that we will discuss soon. This rectangular shape, and I rotate about the x, definitely it will give me a cylinder which has a hole in it, right? To draw that, it will give me a shape like this, a cylinder which has a hole in it, like a pipe, right? It gives me a pipe, correct? You can calculate all these values. They're really easy. Now you have the formula because the cross section of most of them is a circle. But the difficult is my famous function that I'm always using, I used from the beginning of the semester to now, the same shape for you, and you are tired of this shape anymore. My function f of x. Now what's happening if I rotate this function around the x? You see, I'm getting a very kind of different shape. I will get something like this. Like a basin. Correct? And this is my interval from A to B. Here your interval will be from A to B. Correct? I rotated my shape, my function. We are discussing these kind of shapes in this section. We calculate the area or the values of these kind of solid shapes. Correct? The first thing that you see here, my function is continuous. And also my function is bounded. From where? From A to B. It's a closed interval. And I rotate my function about x-axis. Correct? Now look at the cross section. Look at the cross section. The cross section of this function is also gives you a circle. And all the shapes that I draw for you, look, now I zoom out a little bit. I know it gets smaller, but still you can see the cross section of all of these shapes gives you a circle. All of them, the cross section is what? A circle. And the surface area for a circle, the formula is pi r squared, right? For these ones, for the top, for these shapes, we know the formula for all of them from geometry. But for this shape, I don't know, correct? Because the surface area will change from place to places. But if I make it a little bit back bigger, from here to here, that's the radius, the radius r, right? And if I bring it here, you can name your r f of x, right? You know this much algebra. The height is f of x. Then I put a formula for you that the surface area a of x equals pi r squared. And your r is equal to f of x. Then your surface area becomes as a pi times f of x squared. Then what will be the volume? Volume will be integral from A to B pi, even you can write this way, which is not in your book. In your book, they always use A of x, but I break it down here for you. When you are dealing with different functions, pi times square your function always, because the cross section is always a circle. You cannot get like a shape like this when you rotate something, or when you revolve something about the x-axis, you cannot get a shape like this. You will get immediately a circle, correct? Then my formula becomes v equals integral from a to b pi f of x squared dx. Now, using this formula, I can find the value of any given shape or any given function if I want to rotate my function about x-axis, or if I want to rotate my function about y-axis. I will start with few examples here. First, I will rotate my function about x-axis, and then I'll do some examples for you that you rotate your functions about y-axis. One more thing before I forget, we name this method the disk method, correct? We name this method, the name of this method of disks. Why disks? Because you take a small, tiny pieces, right? Each one of them is a disk, right? And you add all of them. That's why we call it method of disks, correct? Because we call this part a disk, right? It's a disk. And you add all these disks. We call this method of disk, correct? Now let's start with few good examples. First, I will do example number 2 in your book. Then I'll go to example number 1. I'll go different way always in your book. I'll change example number 2 as a 1 and 1 as a 2. Let's do first example number 2. In example number 2, find the value of the solid revolution where y equal radical x on closed interval 0, 1. Revolved or rotate, let me use the same term in your book, rotate about x axis. Even for this problem, I'll graph it for you. You don't need to graph, but even this problem, I'll graph it for you. Each one of us in this class, we know what is the shape of y equal radical x from algebra. Correct? The shape of y equal radical x is this shape. I'm not drawing too far because I have a closed interval. I'll name here 1 and I'll name this point 0. Now, this is the graph of y equal radical x, or f, you can name it f of x equal radical x, it doesn't matter. Now, let's rotate this graph about x-axis, because they ask you to rotate this graph about x-axis, right? This is x, this is your y. Let's rotate. Let's graph another one, the rotation. I should be perpendicular, but I'm not perpendicular, right? This is the rotation. When you rotate this graph about x-axis, it gives you a shape like this, and your cross-section will look like this, something. Again, you see your cross-section is what? A circle, correct? Now, your formula, v equals integral from a to b, pi. I made it easy for you, f of x square dx, correct? then I can write a formula to calculate here. V equals integral from where to where? From 0 to 1, the interval is given to you. Keep the pi. F of x, what is your function? Your function is radical x. Your f of x is equal radical x, right? The function is given to you. Now square it, dx. Then v equals integral from 0 to 1 pi. The square root of x squared gives you x dx. Correct? Using the techniques of integration, all of you, after this, you will be fast. V equals, you can put the pi even outside. Pi integral from 0 to 1 x dx, which you can say v equals pi times integral of x gives you x squared over 2. From where to where? From 0 to 1. Or you can say v equals, plug in the values, pi times, if you plug in 1, it gives you 1 squared over 2, correct? Minus 0 squared over 2, which gives you v equals pi over what? Pi over 2, final answer. It means the value of this solid object, it's like a top of a bullet, right? The volume is pi over 2. Easy, correct? Let's take another function. Let's do now your example number 1. Everyone knows that the volume of a sphere is 4 over 3 or 4 pi over 3 r cubed. That is the volume of a sphere. Correct? This is the volume of what? Of a sphere. Let's prove this formula. Let's find through the calculus that the volume of a sphere, a shape like this, like a ball, like a baseball ball or football ball, correct? The volume of a sphere is 4 over 3 pi r cubed. Let's prove it. It's really interesting. I like this example a lot in your book. You prove a formula, which they gave you in geometry at the school like this, ready for you. Okay, this is your formula. Now you can, if I give you the radius, different radius, you can find the volume of different spheres because it's based on the radius. If radius gets smaller, volume is smaller, radius gets bigger, volume bigger. But let's prove this formula, correct? We should know which shape I should rotate about x-axis to give me a sphere. At least you know this much. If I rotate half a circle like this, half a circle about x-axis, definitely it will give me a sphere, correct? And my formula is v equals integral from a to b pi f of x squared dx, right? Or ax dx, but I break it down for you, make it easy for you. You should square your function, then dx, correct? Now, I need a function. You see here, I need a function. What is this function? What is y equal what? What is the function for half of the circle? I don't know what's the formula, or maybe I know, maybe some of you know what is the function for half of the circle, but it's really easy to derive that formula or that function. If I have a full circle like this, what is the equation for the circle? The equation for the circle, if you don't remember, I will write here, x squared plus y squared equals r squared. You learned it in college algebra. You learned this equation and pre-calculus. Some of professors, they are escaping the conic chapter. That's why I always start shouting, don't escape this, because we need it in calculus. Students has to learn this, okay? This is the equation for a circle. Now, if I ask you to write equation as a function, which is again the topic of discussion of algebra, you can write any equation as a function. And I know to write as a function, I have to have alone in one side and everything else on the other side. Then let's solve this equation of the circle for y. Subtract x from both sides, or x squared from both sides. You will end up with y squared equals r squared minus x squared. Let's solve it for y. Take the square root from both sides. The square root of y squared equals plus minus the square root of r squared minus x squared, which I'll end up with y equals plus minus the square root of r squared minus x squared. This is actually the equation for the half of the circle. You see, because you have y on this side. This equation will be the equation for the half of the circle. Do I need to calculate both of them, plus, minus, or just I need to just calculate one of them? Because I'm rotating anyway, right? If this is the equation, y equals square root of r squared minus x squared, this is the top portion, and the bottom portion will be the negative one. I don't need even the negative one because I'm rotating anyway half of the circles around the x-axis, right? Then I'll just use y equals square root of r squared minus x squared, correct? Now, this point in the shape is r, your radius. From here to here, we name it r. Also from here to here is r, and from here to here will be negative r, right? The distance. Now I have all the pieces, and I'll just plug in my formula. V equals integral from a to b pi f of x square dx. It means I'll set like this. V equals integral from negative r to r pi. What is f of x? My function is square root of r squared minus x squared all square dx. Correct? Let's continue. Then v equals integral from negative r to r pi times r squared minus x squared dx. Here you can move out the pi outside of the integral. You can write v equals pi integral from negative r to r squared minus x squared dx. From here on, you have two ways to solve this integral. If you focus a little bit on the shape, what do you see? The right side is symmetric with the left side. Remember the areas that when you're dealing with the symmetric shapes, you just multiply your integral with 2 and you change your bound and you calculate only one side? It's not explained in your book why. I'm showing it here for you because it's symmetric. Instead of calculating all of these, I'll just calculate one side. Times 2 gives me the sphere, right? Then I can write here v equals 2 pi integral. Look, I'll change negative r to 0 because I'm just counting one side. From 0 to r squared minus x squared dx. Don't do a mistake. R is a constant, R is a number, it's not a variable, right? The only variable that you want to differentiate here is X, correct? Then when you do the integral, focus, do not do a mistake, then you can write V equals 2 pi times, what is integral of r squared dx? Think r is a constant, correct? Of course, it gives you r squared x minus integral of x squared gives you x cubed over 3. From where to where? From 0 to r. Let's simplify. V equals 2 pi times r squared times r minus r cubed over 3 minus, of course, when you plug in 0, the other part becomes 0. Even I will not plug in, right? Because you know, when you plug the lower bound, it gives you 0. Simplify. V equals 2 pi times r squared times r gives you r cubed minus r cubed over 3. You need a common denominator of 3. Then 3 times 3 times 3. Then you say V equals 2 pi times 3r squared minus r squared gives you 2 pi r cubed, not a square, over 3. Correct? Multiply the 2 pi to the n side. Then you can write V equals 4 pi r cubed over 3, which you prove the formula that the volume of a sphere is 4 over 3 pi r cubed. Correct? We proved it. Kids are using this formula, or the lower classes of math using this formula as a formula. But calculus, using calculus, you could prove it, right? But please, if a school student or lower classes of math comes to you and ask you, oh, I have a sphere and r is equal 4, can you calculate the area for me? Do not use calculus for them, correct? Because they don't know. Just use the formula for them. It's for you to, we did this proof for you, how to find the volume of a sphere, correct? This was really an interesting example. Now, let's do another example from your book. Find the volume of the solid. Find the volume of the solid obtained by rotating the region bounded by y equal x cubed, y equals 8, and x equals 0 about y-axis. We did about x-axis. Now we rotate this function y equal x cubed about y-axis, and we try to find the volume of that solid shape. Again, I will graph this example for you. Everyone knows y equal x cubed, the graph of y equal x cubed, hopefully. X, y, This is the graph of y equal what? X cubed. Why I didn't put the other part like this? Because the bounds are giving to me from x equals 0 to y equal what? Y equal 8. Now you rotate this shape around y-axis like this. Not about x-axis, because if you do about x-axis, it gives you something x, something different, a different value. If you rotate about y, it gives you a different value. Remember, the values are not the same. If you rotate about x, do it at home, calculate, rotate about x. Then I'll do here how to rotate about y. V equals integral from a to b. Remember, I explained to you, it should be ay dy now, right? Because you are rotating about y-axis. But here I have y equal x cubed. How to take the integral dy? The easy way is, remember this note, every time that the function is given and you rotate your function about y-axis, immediately solve your equation for x, correct? If I solve this equation for x, from here I can write x equals the cube root of y, right? Now I'm in a good shape. If I graph it again for you, I rotate for you and show everything for you. I will get a shape like this. And this one will be my cross section, correct? This height or this radius is actually x equal cube root of y, correct? Here you have 0, here you have 8. Now you can write v equals integral from 0 to 8 pi function, which is cube root of y square, but dy, not dx, correct? Just simplify and find the integral. V equals now V equals integral from 0 to 8 pi. Here, if you simplify, it gives you y to the power of 2/3, right? dy. Move the pi outside of the integral. V equals pi integral from 0 to 8 y to the power of 2/3 dy. Now, finding the integral, you have to add 1 to the exponent, divide by new exponent, right? It means v equals pi times, add 1 to the exponent, 1 plus 2 over 3, multiply, add, which gives you 5 over 3, right? Then y to the power of 5 over 3, divide by 5 over 3, from where to where? 0 to 8. Or v equals pi times 3 over 5 y to the power of 5 over 3 from 0 to 8. Plug in the numbers, then v equals 3 over 5 pi times 8 to the power of 5 over 3 minus 0 to the power of 5 over 3, which gives you the calculation. I'm not going to do the calculation for you. 96 pi over 5. Please continue here. 2 more steps, you will end up with this answer, correct? This was all about finding the volume of a solid if you rotate a function about x-axis or y-axis. Our lecture is not finished yet. I will stop the lecture here, and in next video, I will discuss how to find the volume of a, which we call it washer. The shapes like I introduced to you, like a pipe, right? Something like this. You have a hole inside. These kind of shapes. How to find the volume of those. It will be my next part of discussion. I'll stop the video now and see you next time for 5.2.